Okay, so what do we mean by, listen up, what do we mean by elastic collisions? Elastic collisions. One important thing to remember or to know about elastic collisions, the word elastic here does not have the same meaning as what? As elastic when we did elastic what? Elastic energy, okay? There are no springs involved here. There are no springs involved. Elastic collisions, elastic collisions are basically collisions where not only momentum is what? Not only momentum is, but something else also is conserved, which is kinetic energy. Kinetic energy, okay? So two things are conserved here. Kinetic energy. By the way, which one of those is always conserved? Which one of those is always conserved in any event that happens in the universe? Momentum or energy? Always. Momentum is always conserved. Kinetic energy could be what? Could be conserved or could be what? Could be what? Could be like, wasted or dissipated or lost to the what? To the surrounding or to the system, okay? If only momentum is conserved, you do not call it what? You do not call it elastic. Does anyone know what's the opposite of elastic? English-wise. Go ahead. No, it's actually elastic, but with a prefix before it. Like possible, impossible. What do you think the opposite of elastic is? It's actually inelastic. In, elastic. So whenever only momentum is conserved, we call it what? Inelastic. When both momentum and kinetic energy are conserved, it's called what? Elastic collisions, okay? All right. So this means that the total EK before the collision is identical to the total EK after the collision. By the way, is this realistic? What do you think? Could the total kinetic energy of everything coming into the collision be exactly equal to the total EK after the collision? Do you think that happens all the time? Nope. Very, very, very few cases. Because most of the time, what happens to some of the energy when two things hit each other? It's what? It's lost due to what? Probably. What force can you never eliminate? Friction. Exactly. Because of friction between the two surfaces when they actually bombard or when they collide with each other, some energy is always lost. However, if the energy lost is so small compared to the what? Compared to the total EK before, we could consider it to be what? To be elastic collision. Do you see what I mean? It's a theoretical idealization of what? Of certain collisions. Okay? If no energy is lost within the moment of what? Of collision, we call that elastic. Okay? And by the way, it's not just like it's theoretical and never happens. This actually happens a lot in what? In subatomic particle collisions. When they actually collide particles, many of those collisions are actually what? Are elastic. Okay? Because there is no friction between those particles because their sizes are almost, I want to say, infinitesimally small. Okay? So equation-wise, there we go. Do you have this equation or do you have to write? Okay. So what does this basically say? It says kinetic energy of object 1 initial before the collision plus initial kinetic energy of object 2 plus keep going must equal also the sum for, by the way, do they have to be the same object coming in as coming out in collisions in general? Think of chemical reaction. Do you have the same things coming in as the same things coming out? No, usually you have what? Different products than what? Than reactants. In general, here, you could have, for example, 4 balls, for example, colliding together, and what? Somehow, how many parts come out? Maybe 10. Maybe they smashed each other. So it doesn't have to be the same number of the objects before and after. Also, it doesn't have to be the same object. What you need to know is if you collect all the energy, kinetic energy, before and after, you should exactly have the same what? The same exact entire conservation between them. Okay? All right. So in other words, the objects exchange kinetic energy between each other, but the what? Total EK of the system. Okay? Go ahead. Total EK of the system, of the whole thing, of the system remains the same the whole time. Yes, go ahead. Mhm. Yes, thank you. Exactly. Everyone, Josh basically thought of the bars, right? So Josh is saying, so you're saying that in this system, only one energy is of relevance, which is what? EK. There are no other what? There are no other energies what? Involved. Or if they are involved, they also what? They are also conserved in their own right. Do you see what I mean? If there's thermal, thermal before, thermal after. If there's EG, EG before, EG after. We only care in elastic collisions only about what? EK is the only player that needs to be having the exact same value at every single instant before or after. Okay? All right. So now let me actually show you the two equations that we will deal with. Okay. A few things about these two equations. Number one, obviously you don't have to memorize them. Number two, what is this? A scalar or a vector? Which means what? We're going to make it a scalar, but we're going to also add what to it? Either a what or a what. Every one of those will be made a scalar, but will be made what? Either a plus or a minus. So we will designate a what direction? A positive direction right before we start. Okay? How are those equations actually derived? It's not really that hard. However, to understand how those equations are derived, you need to apply both what conservation, momentum, and what? EK. And then you have to solve what we call a two equation system in two unknowns. In general, you get this answer. Okay? There is no need to go through the derivation. We just want to make sure we know how to use these equations. The other thing, how many objects are only involved in this collision? Just by looking at the V2. Only VI1 and VI2 come out to VF1 and VF2. One last thing about this. This is only for one dimensional. This is only for what? One dimensional, not not like this. Nope. This is only for one dimensional, only happening along one line. Okay? So, by the way, can someone tell me how similar the equations are? They're very similar structure-wise. What are the main differences between them? Just look at the equations and tell me how different they are. But okay, I have a way of memorizing them. Okay, I don't want you to memorize them. But because I know exactly how they're different, I have a way of memorizing them. What's the first difference that anyone can spot? Ammar. Exactly. In this bracket, this one depends on what? M2. However, we are solving for what? V1. How about this one? This depends on what? M1. But we're solving here for what? V2. So that's the first difference. What's another difference? Ahmed. Yes, yes, exactly. In this one, if it's one here, it's one here and two. If it's two here, it's two here and one. Two differences so far. One last difference. One last difference. Here. Yes, the first one, you start with one and you say what? M1 minus M2. How about the second one? M2 minus M1. By the way, all the denominators are the what? Are the same. What are they? M1 plus, which is basically the total what? The total mass of the system. Okay? All right. So let's actually what? Let's see how those equations are applied with proper direction. Okay. So let's look at the first one. Okay. You have two slides for each question. The first slide, we're going to sketch the diagram, and the second slide, we'll apply each equation. All right. A ball of mass, 80 grams. 80 grams. Oh, by the way, everyone, listen up. Here is one good thing about those equations. Everyone, questions. I want you to look at these two fractions. Everyone, eventually, what are you going to do here? You got to divide what by what? Yeah. What are you going to do here and here? You got to divide what by what eventually? Mass by, what's going to happen to the units? Of mass only. Good news. Because the units are going to cancel, you do not need to standardize your mass units for this equation. Do you see what I mean? Your mass here doesn't have to be in what? It doesn't have to be. It could be in what? As long as all the masses are the what? Are the same unit, you are fine. You do not have to make all of them in what? In kilograms. Only because they divide out. Only because they divide out. Yes. Oh, no, yeah. So if you have grams and kilograms, you just have to make a decision. Do you want both of them to be in what? Or, but do they have to be both in kilograms? Not because what? No, because they will cancel out anyway. So the units are gonna what? Disappear. As long as the units are the same, they disappear. Okay, let's do the first question. So a ball of mass, 80 grams, which we will keep as is. By the way, would you rather deal with 80 or with 0.08? I would rather deal with 80. Thank you. That's another reason. Is moving at 7 meters per second. Which direction? West. When it undergoes a head-on, which means, by the way, what does head-on mean? 2D or 1D? Head-on means center of mass are perfectly lined up, which means one-dimensional collision. Elastic. They're telling you it's already what? Which means, are you permitted to use those equations? What if they told you it's inelastic? Can you ever use the equations of today? Never. Okay, so only know that to use the equations for today, either you have to be told it's elastic or you have to what? Like figure out or prove it's elastic to use them. Okay. Elastic collision with a stationary ball. What does stationary mean? What's the speed initially? 0. Perfect. Of mass, 60 grams. Assume the collision is one-dimensional. We always will do inelastic. Calculate the velocity of each ball after the collision. After the collision. Okay. What do we do under the problem? What do we do quickly? Diagram. Sketch a diagram. Okay. By the way, do we know, everyone, do we know which way the two balls would move after the collision? Yet. We don't. So at least we can sketch the after or the before picture. The before picture. Okay. Let's sketch the before picture. All right. So we just need to sketch ball number 1. Oh, how is it moving? Everyone. West. So it's moving that way. So I should sketch a ball coming from this side and one just stationary here. All right, let's do that. And which one is bigger? Sorry, heavier. The moving one or the stationary one? The moving one. So I'm just going to sketch a bigger circle for the first one. So go ahead. Here's, oops, I'm going to call this ball 1. And it's moving this way. And this is ball 2. And it's stationary. Okay, let's put some, yeah. Yes. Okay, let's put some numbers here. Mass of ball 1 is 80 grams. Mass of this one is 60. Speed of this one is how much? 7 meters per second. Speed of this one is what? 0 meters per second. Okay, which direction should be positive? East or west? West. The whole system started with west first, so west it is. You can also say negative will be this way. No problem. By the way, question for you, everyone. Is there ever a way that both of them would move this way after the collision? No way. That defies both logic and what? Conservation of momentum. The initial momentum of the system, vector-wise, was pointing to the west. No way after it would be pointing purely to the east. So what are the two possible choices here? Yes, Josh, give me one scenario. One. So that means this one would move this way, and this one would move what? But in a way that which momentum is going to be bigger? This one or that one? Remember, there has to be a winning momentum here. Which way? Which way does the momentum have to stay the whole game? East or west? Which means if they are going to bounce with this one this way and this one this way, which one has to be of bigger momentum? The number 1 or the number 2? The number 2. Okay, what's the other scenario? Anyone? So Josh gave us one. What's the only other scenario? Yes. Both would go this way, which then definitely both momentums would point which way? West. Okay? So at least there are elimination things you can do to at least say this cannot happen. I'll just focus on the rest. Okay, now let's do the what? Let's do the equations, everyone. So here is the first. Sorry. Come on. There you go. Okay. Ball number 1. V. What's the equation? V1F equals. Okay, first of all, what's my denominator for all of them? All of them. M1 plus M2, the total mass of the system. M1 plus M2. I'm just going to write the equations now. Okay. What's my first denominator? Sorry, first numerator for this one. M1 minus M2. Oh, my bad. M1 minus M2. Okay. That multiplies which speed? Which initial speed, I should say? The first one for the, so V1I. All right. Plus. What about, obviously, we said this one will never change. It's always M1 plus M2. What about the numerator for the second one? Anyone? Come on. 2. Which M? M2, exactly. It's the opposite of this. So 2M2. and v 2I. All right, let's plug in numbers now. Which one is M1? We already had, by the way, you always have to label them. I don't care how you label 1 and 2, but you have to stick with your labeling. What's mass 1? 80. Yep, no need for convergence, as long as they're all the same. Minus 60, is it? Okay, 80 minus 60. 80 plus 60. Okay, what was the initial velocity of object number 1? Object number 1 is 7. Yes. So, oh, plus 7 or minus 7? Yes, it was going west, which means plus 7. I'm not going to take marks off if you do just 7, but I'm going to emphasize the direction dependence of sign. 2, yes. Yeah, exactly. The velocity of this one is what already? So do you have to actually show me any calculation for that one? Nope. You are more than welcome to what? To cross it out like this here if you want now. No problem. I'm just going to write it and write a bracket with 0 just to basically show the numbers to be consistent. 260, I believe, yes. And then 80 plus 60 with a 0. All right. What is that equal to? Well, 80 plus 60 is what? 140. So 80. So 20 over 140 times what? 7. Well, good news. 7 and 140, they divide each other. If you divide 7 by 7, you get 1. If you divide 140 by 7, you get what? You get exactly 20. So this actually will end up being what? 20 over 20, which is how much? Positive or negative? Positive. So what do you conclude about ball number 1? Does it bounce or keep going west? Keeps going in the positive direction, which we already said it's west. Thank you. Positive 1 meters per second. Okay. Let's do the next one. V2F. Okay. How do we start? Well, instead of M1 minus M2, it's M2 minus M1 with the addition below. This one is V2I plus 2 mass 1 now. It's basically the opposite of this equation. M1 plus M2 and V1I. So far, so good? Which one is 0 now, V2I or V1I? Yeah, it's always V2I. Well, in this question, sorry. V2I is 0, V2I is 0. So you know what? Go ahead. You can cross this one out, which means it kills the whole fraction. Awesome. So I'm just going to put 0 here, plus, okay, 2 mass 1, which is 80. Mass 1 is 80 plus 60 equals, sorry, not equal, my bad. I need to still include the speed. Otherwise, it would be a unitless number, which makes no sense. What's V1I? Again, what's V1I? The only speed to begin with. Positive 7. Thank you. Positive 7. Equals. Okay, what do we have here? 160 over 140. 140. 1 second. 140 times 7. So those two would cancel into what? Into a 20. So 160 divided by 20, which is how much? 8. Positive 8 or negative 8? Positive 8. Done. So can someone tell me now how would you use those two values to go back and resketch your after picture? How would you do that? How would you do that? Anyone? Raise your hand. How would you go back? Josh. Yes. So this one loses a lot of speed. This one does what? Picks up, exactly, gains a lot of speed. Such that this goes to how much? 8. 8 meters per second. And this one slows down to what? Okay, I'm going to go back to the slide to finish copying. But my question is, how would you confirm using those numbers that this is an elastic collision? What did we say the only condition for elastic collision would be? Kinetic before equals kinetic after. Okay, what's the equation for kinetic energy? No momentum here, just energy. half mv squared. What's the kinetic energy of this one right here? 0. This is not moving, no kinetic energy. Can you calculate the kinetic energy of this one now? Yes, we can. What is it? Half m, obviously after converting to kilograms, half mv squared. How would you do it here? Same way, but you would have to what? Add them up. You will see that basically what? The same number of these two adds up to the what? The same number for this one. Is it making sense now? If you ever had a question saying confirm that's inelastic or elastic, just what? Just do EKI total before, EKI total after, and just see if it's the same, it's elastic. If there is any less, by the way, could EK final ever be bigger than EK initial? Could it be less? Of course, friction makes systems what? Lose energy, not what? Not gain energy. There you go. You can never get EK final to be less, sorry, to be more than EK initial. Good, awesome. Go ahead. By the way, someone says, in elastic collisions, velocity is always conserved. Is that correct? Is velocity ever conserved? No, only either momentum or kinetic energy. Let's actually prove that velocity is not conserved. What was the velocity before the collision? 7. What's the velocity after the collision? 1 plus 8, which is 9. Sorry, yeah, it's not. So don't focus too much on the velocity. Get the velocity and then incorporate it back into momentum and kinetic energy. Good. All right. Let's go to the next slide. Now both are what? Both are what? Up, but moving before the collision. Not one of them is just waiting to be hit. Okay. Cart 1, or ball 1, has a mass of 1.5 kilograms and is moving on a track at 3.6.5 centimeters per second. Which way? East, so that way. Toward cart 2. The mass of cart 2 is 5, much bigger, and is moving toward cart 1, so there is a collision for sure, at 42.8 meters centimeters per second. Which way? Okay, question for you. Which one is heavier, cart 1 or cart 2? Just by looking at the numbers. Cart 2. Which one is faster, cart 1 or cart 2? Which one's faster? So which one has definitely bigger momentum right before the collision? Cart 1 or cart 2? 2, because it's got both what? Bigger mass and what? Bigger speed. So which momentum is going to win, east or west? Which one? Which one's going to win? Or which one is dominant, east or west? West, because this one has more m and more v. So which momentum is going to win after the collision also as well? Exactly. So now you know, basically those two had to add up to a momentum going west as well. The carts collide, the collision is cushioned. By the way, this is why they call it elastic, because there's a what? There's a what though? There's a spring. Everyone look, listen up. The spring stores the energy and then what? Releases it back, making sure that the EK before and the EK after are what? That's why they call it what? Elastic collision. We always assume that there's a spring involved in the collision, but not in the actual objects themselves. Okay, what's the final velocity of each one? All right, what do we start with? Diagram. All right. Okay, everyone, let's do this. So let's say cart 1 is the one moving east. Sorry, east. And it's smaller. Cart 2. Okay. 5, sorry. 5. Do I need to convert these? Everyone, question. Listen up, everyone. Do I need to convert the speeds to meters per second? Do you think do I need to? Do I need to convert the speeds to meters per second? I don't. But if I don't, if I keep them in meters per second, that means also my final speeds will be given in what? Is that fine? I think so. Probably we're going to end up with a lot of decimals if we convert. Let's keep it the way it is. Awesome. So 42, sorry, 42.8 centimeters per second. Okay, this one is 1.5. And how much? 36.5 centimeters per second. Okay, which direction do you think is, again, which one did we say is going to win, west or east? west. So that means we should also designate west to be positive this way. All right, we're ready for the calculations now. Okay, let's start with the first equation. Does it really matter? We have to do both. Okay. All right. So V1 final equals mass 1 minus mass 2 m1 plus m2 V1I plus 2 mass 2 over m1 plus m2 V2I. Okay. Is any speed 0 or no? So nothing zeroes out. Everything stays. All right. Mass 1. We said mass 1. Which one was mass 1? Oh, did we label them or not? Did I forget to? Or? I did. I did. Oh, okay. So we labeled this one. Okay, fine. No problem. Okay. So mass 1 is 1.5 minus 5 over 1.5 plus 5. Okay. What's the speed of object 1 before the collision? Negative or positive? Negative. Okay. So negative 36.5 here. Okay. Positive. Plus, I mean. 2m2, which is 2 times 5 over 1.5 plus 5. The speed of this one was positive 42.8. Okay. What do we have here? We have, interesting, we have negative times negative. All right. So we have here, sorry, what's negative 3.5 over 6.5 times negative 36.5 positive plus, I mean 10 over 6.5 times 42.8. Okay. Who's got this number for me? The whole thing, this part. This times that divided by 6.5. It already has to be positive because there's a minus times a minus. Who's got this? Yes, Josh. It should, remember, it should be big. Look, you're multiplying 36 by 3.5. That's over 100, right? And then divided by 6.5. So I'm saying maybe 16 or 17, something like that. What'd you get? Okay, hold on. What do you have? Go ahead. But no. But what is it? That seems to be too big, just by the scale of the numbers. That's all. Go ahead, do it again. Just these two. Oh no, just step by step. Yeah, I want to just squeeze it to 2 steps. So what is this one only here? 16, 17 something? 19 point? 65. Plus, what about this one? Come on. 42.8 times 10, which is 428 divided by 6.5. Should be 70 something. 60 point 84 85. Okay, perfect. Equals 65 plus 20, 85. 85 and 65 is 15, 50, right? Wow, that's the speed of ball 1. Is that negative or positive? Hmm? Positive. So that means what? Which way did ball 1 move after the collision? West. So did it keep going in its original direction or did it bounce? It bounced. Okay. Why? Because it had a smaller mass and also what? A lower speed. So that means it actually what? Within a few milliseconds decelerated and went back. Yes. Yes, sorry. So what's the sigvig situation? It's 2? Why 1? Ooh, 5. Yeah, it should have been at least 5.0. Let's keep it to 2 sig figs, okay? Everyone, everyone, go back to the question and 5, make it 5.0. 5 kilograms, everyone, 5 kilograms, guys. 5 kilograms, make it 5.0. Just to make sure that at least we have 2 sig figs. 1 sig fig is very bad. So what would this be to 2 sig figs? 86. Thank you. All right. Number 2. V2F. M2 minus M1. V2I plus 2 mass 1. M1 plus M2 V1I. All right. Let's go to the numbers. So now it's 5 minus 1.5 and 5 plus 1.5. What's V2I? Well, I have all the numbers here. It's positive 42.8 plus 2, 1.5, my bad. 5 plus 1.5 times negative. Okay, 5 minus 1.5 is 3.5 as well. So this should be 3.5 divided by how much? 6.5. By the way, what's going to happen here? Which is going to win? So negative 10, I mean 3. What would the final answer be? By the way, is there a possibility of the big ball bouncing? Is there a possibility? Yeah, as long as the west momentum wins, it could actually outbounce. But apparently, not according to these numbers. 42 times 3.5 is going to win over 36.5 times 3. So it makes sense. Yes. No. They have to be the exact same ones from before. Because remember, you are still going back to the what? You are still going back to the what? To the original diagram for the velocities, which means whatever direction they kept as positive from before will also stay the same. We did. Oh, is it because they're next to each other like this? Maybe? Oh, no. Remember, it's direction. This one is moving this way, and this way is positive. And this one is moving this way, and this way is negative. Make sense? And again, Nora, a good question, but remember, since we already used it this way, we have to use it the same way all over. Okay? Josh, what's up? And then Ahmed. Oh, do you have the final answer? Okay, what do you have as a final answer? Full thing. 6.2. What do you have? 6.2? Negative or positive? Positive, because this one wins over this one. This one has no effect because it's the same for both. So it's like a control experiment. So positive 6.2 centimeters per second. What does that mean? What happened to the big sphere? Does it still go forward? But what happened to its speed? So this one, everyone, this one went from 36.5 in one direction to 86 in the other direction. This one lost from 42 meters per second, sorry, centimeters per second to 6.2 centimeters per second. Okay, that's it. So how would you sketch the one for the after picture? Anyone? How do they go after? Yeah, Ammar. They both go this way, but number one has a lot of wind effect, and this one has what? What happens to the wind? It diminished so much because it slowed down. All right. So 2 would be just a little bit, and this one would be just flying to that side. 6.2. What was it? 80. How much? 86. Thank you. Okay, everyone. Last problem is homework. But just so you know, what would you do if you did not look? If you did not memorize or even have these equations, what would be the only other way to solve these two problems? How many things are conserved for these problems? Two things. What and what? Kinetic energy and guess what? You have to actually set up an equation for momentum conservation, which you're not going to be able to solve. You know why? Because you don't know the what? You don't know the final velocity for object 1 or the what? Final velocity for object. And then you have to set up an equation for what? The EK conservation between initial and final, which you also can't solve by itself because you also don't know what? The final velocity for object 1 or the what? Or the what? Final velocity for? But at least you have how many equations? How many? Two equations. One came from momentum and one came from what? Kinetic energy. And you have how many variables to solve for? So there are what? There are ways to do this. But this already includes all the work done. Do you see what I mean? This already includes basically the whole derivation of the method. You just have to use them. That's all. Okay? How many people did the sine law and the cosine law? Do you remember how it was derived? Do you know how to use it though? There, exactly. No need to know how it's derived. You need to know how it's used. And that's today's lesson.